Greetings. I'm going to talk about the conservation of energy and how you can use it to calculate final velocities for an object, and which will give us actually alternatives that we didn't have before in terms of how to compute certain things in some cases where acceleration is not constant. So basically the idea is, and I already mentioned that we have two types of energy. We have kinetic energy, which is defined to be 1/2 an object's mass times its speed squared. And we have potential energy, which on the Earth is a function of height, is given by mg delta h. This is the same thing, if you remember, is the equation for work that it takes to lift an object to a given height. Well, if you think about it, if you're putting that much energy into lifting an object to a certain height, you're giving the object that much potential energy. The way it works in conservation of energy is that the idea behind it is that energy cannot be created or destroyed, but it merely changes form. And if we assume no loss due to friction, then the energy is either potential energy or kinetic energy, and it can convert from one form to another. Okay, new slide. So basically what that means is that if you have, let's say, two states, you have an initial state, so I'll say you have an initial amount of potential energy, an initial amount of kinetic energy, and you add those together, and that's your total energy. Your total mechanical energy is called the sum of those two. Okay, that's initial. And then final, you have the final potential energy plus the final, plus the final kinetic energy and this would be your initial total mechanical energy, and this would be your final total mechanical energy, TME. Alright? So that's what conservation of energy tells us, that what you have in the beginning is equal to what you have in the end in terms of energy. So now let's try to apply that to a situation, and I'll show you what we can do with it. Another new slide. Let's say, for instance, that you have a ramp. This is what you're going to be seeing in lab this coming week. Let's say you have a block on the ramp, and the block is sliding down the ramp. And you could say that the block starts out with an initial velocity vi and ends up with a final velocity vf. You can say that the initial height of the ramp is h, h1, or h initial, and the final height of the ramp, we could say, is h final. So if we apply the previous equation for the conservation of energy, that tells us that the initial potential energy, which is mgh1, or h initial, plus 1/2 m v initial squared is equal to mg h final plus 1/2 m v final squared. Okay, so this is the conservation of energy, and all I did was I expanded the potential energy and kinetic energy terms to reflect what they're comprised of. And probably one of the first things you'll notice is that the masses all cancel out. So mass goes away completely. And what I'm typically interested in finding is my final velocity. So it makes sense, perhaps, to solve this equation for final velocity. So what I'll do is I'll subtract minus g times the final height from both sides. And then I'll divide by 1/2 and take the square root. So I'll just take this step by step. So I have g times h initial minus h final plus 1/2 v initial squared equals 1/2 v final squared. Alright, and then I'll see if I can fit the next one down here. I have multiply both sides by 2, so I have 2 g times hi minus hf plus vi squared equals vf squared. That might look familiar or similar to some other equation we've had, a kinematics equation. There is an important difference though, which I'll talk about in a minute. And then to find the final velocity, you could take the square root of both sides. Alright? So this can actually be simplified a bit. Very often, not always, but very often, you might have an initial velocity that may start out to be 0. Doesn't have to, but it often will, like it will in lab next week. That makes this term go away if that's the case. And then it often makes sense to make your final height 0, so that your initial height is just the height above your final height, and your final height is 0. It makes that equation simpler. In which case, your final velocity becomes simply the square root of 2 times g times the initial height. Okay, so we could do examples with this. Let me give you one. And one of the things I want to point out is the initial height is just this height right here. It has nothing to do with this. This is the important part. This initial height could be this, and it would be this in this case. It would also be this in this much steeper case here. So what I'm saying is the final velocity of the block at this point will be the same in case 1 as it is in case 2, if this initial height here is the same. The block ends up at the bottom in both cases and it starts from rest at the top. It's going to end up at the same final velocity in this case as it is in this case. Alright, so let me just go to another slide, and I'll just write that out. I'll say v final is equal to this square root of 2 times g times h initial, which assumes vi equals 0 and hf equals 0. So if the object started from an initial height of, let's say 5 meters, you're starting, let's say, up at a height of 5 meters, and you slide down a frictionless surface, and I'll say and friction equals 0. It's another assumption here. And this is 5 meters tall. Then square root of 2 times 10, take g to be 10, times h initial is the square root of 10, I'm sorry, square root of 100, which is 10 meters per second at the bottom. Alright, so that is the conservation of energy applied so that you can find the final velocity. And what it does is, and I'll just give you one more slide briefly, the final velocity is going to be the same in this case as it is in this case, as it is even in this case. If friction is 0. Okay, that's it for this one.